Hello, physics students. We're continuing with the physics class. And for those of you who are just joining us, we are using this physics book here. It's the fourth edition of Physics by James A. Walker, and we're just covering volume 1 in this Physics 2AG class. Today we're working on chapter 3, vectors. So remember that I said that a scalar is just a number, whereas a vector is a number with a direction. So examples of scalars were like $5 or 25 kilograms. But examples of vectors would be 10 meters per second going in the upward direction, or a push of 15 newtons to the right. So we're including a direction there, and so we have vectors. Now, we're going to have notation to indicate vectors. So if you see a symbol like A or X with a little vector arrow over it, that means it's a vector. So V, all by just like this, would be the speed, the scalar speed, whereas V with an arrow over it means the velocity, because now it has a direction. Now, it's difficult or expensive for publishers to put little little arrows over all the symbols. So instead, to save money, what they often do will be just to bold the letter. So if you see certain symbols in a research journal or some textbooks that are bolded, they probably mean that those are vectors. Now we're going to be diagramming our physics problems. So we're going to show forces and motions and so on. And so to show that, we're going to use arrows. So vectors are represented by arrows. And the length of the arrow represents the magnitude, the size of the vector. For example, I could have the motion of a car going east at 10 meters per second, and that would be represented by an arrow of a certain length. When I drew these notes originally, these were exactly 10 millimeters long. So on this scale, 10 millimeters represents 10 meters per second. If the car is going twice as fast, then the vector is twice as long. So more examples. Here is, this could be a car going north at 30 meters per second. So I made this vector here. See if I can draw a straight vector now. Not so easy. Okay, so that's a vector that is 30 millimeters long with the scaling I'm using right now. And so that represents the car going in that direction at 30 meters per second. Here's another example. I've got a rock falling at 10 meters per second, so I drew a 10 millimeter long arrow pointing down. Now, all of my examples so far have been velocities, but vectors represent other things as well. They can represent displacements, they can represent accelerations. So here's an example of an acceleration. When a rock falls at sea level, it accelerates at 9.8 meters per second. And so I've got a acceleration vector of 9.8 meters per second squared. I made it 9.8 millimeters long. Actually, it's hard to get it exactly 9.8, but whatever. So that would be an acceleration example. And then here I've drawn a vector which is 25 millimeters long, and it represents a rock that's fallen 25 meters with the scaling. Yet another example, I've got a shopping cart which is being pushed with 25 newtons of force to the left. And so I've got a 25 millimeter long vector pointing to the left. Now, the scaling is purely arbitrary, right? You could decide some other scaling. You could say, 25 newtons will be 2.5 inches long, or whatever you want, whatever is convenient for you. Now, so far, all of my examples have been just in one dimension, either left or right or up and down. But you can have two-dimensional displacements or forces or whatever. And so that could be, here, just going with examples, here's a car, let's say, going at 30 meters per second northeast. So I'm drawing a diagonal vector, right? Because in general, north is represented by being up on a piece of paper, and east is represented by going to the right on the piece of paper, just like a map. Here is another example of force. And in this case, I'm saying that it's a rock which is right here, and it's feeling a force that is up and to the left of 25 newtons. And so I drew this thing 25 millimeters long and up and to the left. Continuing with the vocabulary, magnitudes. We already said that the word magnitude means the absolute value or the size of a vector. So let's just going with an example here. I had a vector which represented 25 newtons up and to the left. Well, the magnitude of that is the 25 newtons, and we're taking away the direction piece of information. And when we write that, we can write it as putting, you put the absolute value bars around your variable, your vector, and that gets you the magnitude. Now, as a shortcut, what we will do is say that if you have something that you know was a vector to begin with, and you write it without the vector sign, right? If I get rid of the vector sign, that's equivalent to just to doing the absolute value, let's say, and we just say, okay, that's the magnitude. So a vector symbol that is missing its little arrow, that means the magnitude of that vector. Now, the next thing we need to learn for vectors is the process of finding the components of the vector. So in the previous example here, this vector is going up and to the left. And so we say, well, it has an up component and a down component. So that means that the components means the parts of a vector. And the parts of a vector are always going to be 90 degrees in different directions. So we would have, for example, we could say the components of some vector on a map is a east going part and a north going part, or maybe an x direction part and a y direction part. And so we want to learn how to find the components. By the way, the words finding the components, there's another term for that. It's called to decompose a vector. So the word decompose means finding the components. So let's have some examples. I've got a car going northeast at 30 meters per second. What are its components? So here is, you start out with just the vector, right? It's a vector that you've drawn on a piece of paper, and you want to find its component. So your first step is to draw reference lines, and the reference lines need to be at 90 degrees to each other, and the usual thing is to make one of them be horizontal and one of them be vertical, up and down. And you want the reference lines to touch the two ends of the vector. So we're going to have one like this, and we're going to draw our reference line. Boom, 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 boom. This is our horizontal reference line, like that. And then another one, a vertical reference line, and it's got to touch the other end. Boop, 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 boop. I'm trying to be careful here. And okay, so we've done it. We've drawn our two reference lines. And then to find the components, we draw the vectors. The first one that starts at the tail and follows the first reference line. So let's see. I've got my first one here, so that's part of my answer. And then we continue with the second component, the vertical component. We continue in the upward direction here, and that is the second part of your answer. And so, okay, we've got our answer that these two components are the parts of the northeast pointing velocity vector, like that. Right, so we've drawn them, and now maybe we want to know the magnitudes of the components. In fact, very often, or maybe even usually, we want to know how much of a velocity you've got in one component, the east component, and how much velocity is in the north component. So in this particular example, I kind of chose a very simple case. It's made simple by the fact that it's going northeast. And northeast is equally in the north direction and the east direction. So that means that the length of the magnitude of the east vector, the east component, and the magnitude of the north component will be equal. And in that case, we can use the Pythagorean theorem to get to the answer. So we know that this part here, this magnitude squared plus this magnitude squared is equal to the magnitude of the original vector squared. So v east squared plus v north squared equals v squared. And the two components are equal, so this, you see, this is v east squared, and then this is equal to v east squared, so I have 2 v east squared, which equals v squared, and I divide both sides by 2, and I take the square root of both sides, and so I find out that the magnitude of v east is the square root of 1/2 of the magnitude of the original velocity. This v here is not inside the square root, right? So sometimes this question comes up, right? Like that. So that's supposed to be a parentheses. Okay, and so, the square root of 1/2 is the same thing as 1 over the square root of 2. A little algebra there. And putting that into a calculator, you get the answer that the magnitude of the 30 meters per second northeast, the magnitude of the east component is 21.2 meters per second. And the north component is equal to that. It's also 21.2 meters per second. And that's it. We've done it, right? We found the components of this velocity vector. Hooray.